So using the same target analogy, starting back over on the left, we've got, under the new definition, high trueness, low precision gives us low accuracy. In the center target, low trueness, high precision gives us low accuracy. On the right, under the new definition of trueness, we've got high trueness, high precision, high accuracy. Okay, so it's just a little slightly different thing, um, and different terms that we're using based on ones that we're familiar with, but we're adding in this idea of trueness. Okay, and if this is just a little bit confusing, just remember that what we're most interested in geospatial work is that our information matches as close as possible whatever is out there on the Earth's surface, um, natural physical landscape characteristics or human demographic characteristics, that at the time those measurements are made, that they're matching reality as close as possible. That's what we're looking for. And that if you went back and did it again, it would be as close as possible. The methods that you use to collect the information are getting accurate measurements and observations of whatever it is that we're interested in on out on the landscape. And to finish off this little topic, trueness versus precision. Trueness measures your bias. Precision is a measure of spread. So, looking at the diagrams here, we have true but not precise in the upper left-hand corner. Lower left-hand corner, not true or precise. In the upper right, it's precise but not true. And in the lower right, we have both true and precise, accurate. So, when we're looking at accuracy, we need that trueness. We need it to be precise, on target. Again, the concept is matching the reality that exists as much as possible in your data set with whatever numbers we're using to measure that phenomenon. And again, we're switching gears. The next major subtopic we're going to be exploring here is just this general idea of errors. And why do we care about errors? There's this great acronym that came out early in computer science, GIGO, garbage in, garbage out. Your computer and the algorithms and procedures and protocols that you use to analyze data may be wonderful, but if your data is garbage going into the system, it's going to be garbage coming out of the system. You can't really clean it up. Okay. So, kind of the example that I normally use in classes here is we have these 5 hypothetical data sets being thrown into an analysis, and we don't necessarily need to know what the analysis is in order to understand this. But if we have 4 data sets that are accurate, they have trueness and precision, and we have one of our data sets going in one of the inputs is just flawed. It's horrible. It's got errors. It's just not really good information at all. No matter what we do, if we include that information if we include that 5th data set in the analysis, the information that we generate, the results, are going to carry those flaws forward. And that's not something that we would like to see happen. In GIS work, and just as an ideal, as this ideal construct of we want to create information that's good and is as accurate as possible. But always remember, and one of those things that people don't necessarily like to think about, but out in the work world, one of the things that we are doing is producing information that people are using to make decisions. And if other groups don't like those decisions, quite often they can be challenged in court. And so if we're using flawed information as an input, that can be a target for the opposing counsel in court to tear apart your work and basically invalidate whatever decision it was, nullify entire projects or programs, and then force things to go back to the drawing board and start over again. This is what often happens when groups might be challenging governmental actions on environmental impact statements, for example. If there's maybe a hypothetical timber sale occurring in some national forest, and local and regional environmental groups don't want that to happen because they're interested in preserving the environment as it is or minimizing the impact of human activities on the environment, one of the ways that those organizations can go in and basically attack those decisions and say they were flawed decisions is if they can demonstrate that you were using flawed information as the foundation for the decision-making process. That can invalidate, years worth of work. So it's very important. Why do we care about errors? We want to minimize them as much as possible. Okay, and again, it's a great ideal to uphold, but it has legal ramifications too. I mean, there are big problems that can happen if you use flawed data, and if you intentionally use flawed data, that's even worse. So we just don't do it unless you just don't. Just don't go there. So in the end, again, this acronym garbage in, garbage out. One of the inputs is flawed. The entire analysis is flawed. Okay. Now, does that mean that anytime we come across an error in a data set, we have to throw it out? No. It means that there are acceptable levels of error that can be inherent in a data set. And we know that not every data set is perfect because no data set is. Everything has some amount of error built into it. But if you're using something that's just terribly excessively flawed, and as you get familiar with GIS data in taking more classes or working in it, you'll get a feel for noticing where the information is flawed. For example, the easy thing would be, if all of the locations in a point data set, so this one right here, this cities data set in this analysis is wrong. Let's say all the cities are in the wrong location, off by as much as 10 miles total. And if you apply that to all of the cities here, which are all capitals across the United States, then the analysis that you're doing carries that much flaw in it, that much error in it, and that's really not acceptable. That's not an acceptable level of error. If the city location was off by a foot, no one's going to care about that. That's not a big deal. That's well within the margins of acceptable error. And that particular kind of error we will explore later in a slide in this lecture set. But in general, the principle that we want to use, the best practice, is to use the most accurate data sets possible that were produced using defensible, rigorous scientific techniques, established protocols, established procedures that are known to work well using very well accepted mathematical and statistical processes. And as long as that's what you're always working under, using the best and most accurate data possible, you are going to wind up with results that are inherently less prone to having major errors. Okay, you're going to be working all the time to reduce and minimize the amount of error in your work. And the best way to do that is to use good practices of analysis and to use very accurate data sets. So, what are the kinds of error that we run into out there in the world? Here's a short list of them, but some of the more important ones in some of the larger categories. Attribute error, what is it? Positional error, where is it? Topological error, which is how well the pieces of vector data match up with each other, and are they linked to the Earth's surface properly or not. Temporal error is timing or time errors, and then there's a couple other ones: the ecological error and modifiable aerial unit problem. And we'll explore each of these in slides that are coming up. Some in more detail than others. So again, drawing on statistics in general, just as a refresher for those of you who've gone through stats classes, here's some of the things that you might do um, to check your work afterwards. And since we're looking at space inherently, these are spatial methods of looking at how well your work represents reality. So if we generate a new geospatial data set, a map of something, and we want to know how accurate it is, and how well does our work match what exists out on the landscape. One of the things you can do is a simple random location, spot checking things on the map, just randomly generating numbers or throwing darts at a map or something like that to say, let's check these locations to see, are they accurate or not. And that is not a very, high level of validity in checking work. So there are other methods that we can use that are a little bit more rigorous. So we start thinking about applying methods from other sciences and incorporating them in here, or from statistical science and applying them to the spatial realm. So random sampling, we could, for example, break up a map into different sections and then randomly select sections and check those to see how well the work matches what's on the landscape. You can do a stratified random sample, which would mean breaking up clusters of the same thing. So maybe we'll sample 5 locations that we think are supposed to be forest. We'll sample 5 locations that we think are supposed to be urban, 5 locations that should be water, and so forth and so on. And so you just do a number of those by groupings of major land covers, and there you're stratifying your random sample, which is more rigorous. And another one would be systematic sampling, which would be maybe we're going to sample point locations at every kilometer across a grid through the map that we created, and we're going to do every single one of those systematically across the whole area to see whether or not our outputs match what's on the Earth's surface. And that's the whole idea behind doing this. What's here, this attribute error checking. So when we generate a map, the contents of the map are spatial attributes, some kind of environmental characteristic, human environment or human demographic environment, physical environment, excuse me, or human demographic environment, something about that. And so we want to know how well it matches what's out there. So we're going to go through an example of a type of attribute error checking in the next few slides. So drawing upon satellite image analysis, here's an example of a simple land cover classification. So taking a satellite image and imagining that we're only interested in 3 land cover types: urban, forest, and agriculture. And the error matrix tells us something about how accurate our work is. And basically, the work that we do ahead of a satellite image classification, ideally, you send a field crew out, and the field crew makes observations of those different land cover types with a GPS, so you know where those locations are in space. And we use that information to train the satellite image analysis program and tell it, all right, here are locations that we know are certain land cover types. And based upon the characteristics in the satellite image, go find everywhere else in the image that matches those characteristics, and then produce a map that splits the image up into those different land cover types. So it takes a very complex combination of characteristics and it breaks them down into simple categories of land cover. So how do we read this error matrix? Let's start looking at the rows going across. And the first row is urban. Okay, so we've got columns of urban, forest, and agriculture, and then a total. So there are 4 numeric entries across for urban. 22 locations that we knew were urban were classified in the map as urban. 2 locations that we knew were urban were classified as forest. 2 other locations were classified as agriculture. So out of the 26 locations that we knew were urban, 22 of them were classified properly on the map. Look at forest as a row going across. 23 locations total we knew were forest. 2 of them were classified as urban. 19 were classified correctly as forest, and 2 were misclassified as agriculture. All right. Then our last land cover entry, agriculture. We had 27 locations we knew were agriculture. 3 were classified as urban. 4 were classified as forest. 20 were correctly classified as agriculture. Okay. So over on the far right, we have row totals of how many of those locations there were. And across the bottom, what we're looking at is totals for each row. So how many of our locations in the first row under urban, how many locations were classified as urban? 27. How many were classified as forest? 25. How many were classified as agriculture? 24. Okay. So we use those row totals and column totals in the next 2 slides. But for now, what we look at across the matrix is where each row and column meet the same land cover type. That's the number that were classified correctly. And so we use that, we add those together, divide by the total number of locations, and it gives us the overall accuracy of the image. So the land classification map that we created, the classified map, given the accuracies of 22, 19, and 20 out of 26, 23, and 27, basically the total 76. So that sum divided by 76 gives us 80.2% overall accuracy. So our map was 80% accurate in matching what we observed as being urban, forest, and agriculture at locations on the Earth's surface to what the algorithm produced when we told it to create a map. Okay, so an error matrix like this is something that we often will generate when we classify satellite imagery or air photos or even drone imagery these days. Very commonly used and applied to nominal and ordinal levels of data out in the landscape. So it's really, it's a little bit complex to think through and how it works, but overall it's a pretty simple statistic to calculate. As long as you do the work ahead of time and you do very good field work, so you know for sure what's on the landscape, and then it helps you better interpret when you create the classified map what the end result is. Error matrices also get used to generate a couple of other measures of accuracy beyond the overall accuracy of an image classification. One of those is the producer's accuracy. This occurs when the map maker is omitting observations from classification. It's known as an error of omission or an error of exclusion. And how we calculate it is we look vertically down the columns and we take the number of correct observations divided by the total in that column, and that gives us the producer's accuracy for that land cover type in this example. So urban with 22 correct over 27 total, 81%. Forest, 19 correct over 25 total, 76%. For agricultural land, 20 correct over 24 gives us 83%. So we have an overall accuracy of 80.2, but individually, each of these cover types has their own accuracy, known in this version as the producer's accuracy.